cycloid, and maybe I'm going to put one of these up here on the board or on the overhead, and we'll look at it, and maybe you folks could pass those out to everybody. And let me have the remainders. And then I have a second one here as well. Okay, here I want to show you this. Here's what we did last class session. Okay, so here's an image of the rolling wheel, rolling ball, with the associated equations. And my drawings are slightly different in the approach I took on this handout. So what you can notice here is the description for X. Here's the point P that we're trying to monitor right here where my pen is pointing. So from this defined origin here at the ground, where the wheel is touching the ground, if the wheel is rolled forward, then it's lifted this point up. It's lifted this point up, and that point now is up here. And here's the arc length of the wheel that was raised up off the ground, and that arc length is laid down here on the ground. The tread that was just lifted up here is laid down on the ground, was laid down on the ground there. And there's the rotation angle theta. And so as I said yesterday, or last class session, the x distance here to get to point P from here is S, get you over here, and then you're going to back up the sine of r times the sine of theta there. So that's where we get this expression, S minus r sine theta, but S is r theta, and then we clean that up and factor it, and here it is. We then crank the derivatives on it, and we get the acceleration and velocities. Similarly on y, the height y here is you go up to r, and then you're going to back down r cosine theta right here to get to the y reading and differentiate. Now what I did on this handout is I took those values at important points in the cycloid's motion. And I'll get this so that it just fits on the screen here. Okay, so all the detail is there, and let me see if that helps with the focus any. Okay, so what you can do is you can study this drawing with these key values here at these different locations to help you understand the motion of this cycloidal path. And you can look right here when the wheel is just, the bottom of the wheel is touching the ground, it's got, the only acceleration it's carrying is r omega squared, straight upward. Straight upward. When the wheel finishes its complete rotation, that point has come back down to the ground, and it comes in vertical, and its acceleration right there is upward again. And what you also want to notice is in this portion of the path that here's the acceleration when the point on the cycloid is exactly at the same level as the center of the wheel. Here's the acceleration terms back to the left here. And what I did in this example is down at the very bottom it says alpha equals 0. So I gave the wheel a constant angular velocity just to make life a little simpler. And so when the point on the edge of the wheel is at the height of the center of the wheel, the acceleration is r omega squared to the left. And you can see that the component of it that's tangent to the path here is behind the velocity. Here are the velocity components. And so you can see that it's decelerating. Conversely, as that point is rising on the cycloid, here's the acceleration at the center when it's at the height of the center of the wheel. And you can see that the component of the acceleration is along the direction of the velocity, so it's accelerating right there. Acceleration, deceleration. Okay, so it slows down as it's coming across the top. Remember last session we talked about the speed at the very top of its rotation is twice the speed of the wheel moving forward, and it slows down till it comes in with a zero velocity down here, and then it lifts off again, comes back up. Okay. The second handout I gave you is similar. More of the same. And I carefully drew it. And calculated the velocity. Here's the speed that it has at any location. So I just took the kinematics, like you had in the last quiz, the rectangular kinematics, and worked up the speed in terms of the omega and theta for any location theta. And here is distance r, little r, from the pole. From the pole, being the origin of coordinates over here. So no matter where you are on this path, here's your distance from the origin. And then down below here is the acceleration expressed in terms of generalized alpha, the geometric theta, and omega. Any questions? It's pretty straightforward. And then finally, in a tabular form, down here are all those values at different locations as far as the amount of rotation that's occurred. Okay, so that's a pretty exhaustive coverage of the cycloid. Now, let's see. Someone, Dylan, you had a question from?
Got it figured out.
Okay, good. So we won't respond to it then if you got it figured out. And Alfred, I passed out a solution key to the quiz. Well, anybody else come slipping in late? And yeah, there's another one there. Nope, sorry. There you go. And I'll get those quizzes back to you folks next Tuesday. I think it would be worthwhile we have enough time today to do something else here with the absolute motion. Here's a problem that's in your homework. This is a classic. You may have actually played with this in physics, something like this. You can go home and take a spool of thread and play around with it a little bit. And this motion relates to the cycloid understanding that we just talked about. So if we have a spool of cable or thread and we're pulling the underneath of the center with a velocity, we're pulling the cable out at a speed of VA, then the question that's asked here in your homework is what the initial speed, let's see how they do this problem. We got a velocity to the right, compute the velocity of the center O of the wheel and the angular velocity of the reel. And they gave you a hint. I wish they hadn't said that. be careful not to make the mistake of assuming that the wheel rolls to the left, because that's the classic thing that people think of. Except for you folks. You wouldn't think of that, would you? You know it's going to go, you know it's going to go to the right. Why do you know it's going to go to the right? It's not slipping, so this point right here is, where my pencil point is momentarily what? At rest. This is a single rigid body, which means every point must be rotating about that point momentarily. If the center is moving at a speed VA, which they gave us, then everything, we're trying to figure out what the center is doing up here. The center must then be moving in a proportional scaled value related to that VA reading right there. And here's the speed of the top of the wheel. Okay, I think I got that dark enough that you can see it. Okay? And you know the geometry based upon the radii or the diameters given over here on the left. And so therefore, you can just scale that and divide. You can take this VA value divided by this little length right there, and that's going to be the omega. Okay. So this wheel is rolling clockwise. Okay.
The omega about, the omega about the base, not about the center.
No, doesn't matter. There's not about, and the omega is not about any location. This is a rigid body. I could etch a line like this on there, or any direction I wanted, like that. And that line is in rotation with an omega reading. That is constant, is the same for no matter where we are on that. Okay. Let's see, number 37 I think is assigned also. That's actually one I kind of wanted to do, but I don't think I'm going to do it with you. Maybe we should take a look at this one over here though. We have a little more time on this today. Here's a nice looking mechanism. We're driving this circular disc to the right. We're driving this disc to the right here. And that's going to be causing this arm OA to lift up and move clockwise. And when this arm over here is moving to the right at speed v, we want to get an expression for the angular velocity of this member. Okay, now again, we're doing what type of analysis? Absolute motion analysis, which means we need to write a geometric relationship. Need to write a geometric relationship that describes the relationship of the quantities in that picture and the variables in that picture, and then see if we can figure out how to come up with the angular velocity of OA. Okay, so we have a defined x distance from the right-hand pin O over here to the left, and then we got a radius of this disk, and then we have this arm that rests up against it. So let's draw that on the board. Yes, disc rotates. And then this arm lays up against that. It's out here, pinned. And then that arm is resting up against this, like this. Okay, and they told us that the center of this disc is at distance x from the fixed pin over on the right, which I think was O, and I think A was the contact point up here. Other way around?
No, it shows A at the very top of the lever.
Okay, well, it's the arm. It's the member OA. Okay, thanks. And then they're giving this center of this wheel a velocity to the right called V. And we're looking for omega of OA. And they also gave us the radius of the wheel. Happens to be R. Suggestions? Excuse me? Geometric relationship. Mm-hmm. What do you want me to draw? Anything else on here?
A radius between the center of the circle and the contact point.
Okay.
And noting that that's going to be a right angle up there.
Good. Nice. We like that. Everybody happy? Anything else we should put on this? Our goal is this. Which is the theta dot of that member. Thank you. Just fishing. So theta here. Okay, we like that. And somebody said law of cosines or something like that. Necessary?
Yes, but
We could use it, but why use it if we don't need to? If it's a right triangle, we don't need to use law of sines or cosines. Okay, so again, we're looking for a geometric relationship that ties the given data, here's the given information here, part of it, and something that leads us towards the thing we're looking for, which is that theta dot. So we need to tie this given piece of information with that variable. And I think you all realize that x dot relates to this given v. And so we could include x in our geometric relationship here with a fixed r. It looks pretty nice. It's a sine relationship. So we have that the sine of theta is equal to r over x. I try to avoid using the quotient rule just because it's cumbersome. And so what I'd do is I'd probably rewrite this way and differentiate this with respect to time. So we get x dot sine theta plus x cosine theta, theta dot equals 0. And we need, here's something that might be useful. Remember, we're trying to come up with omega described in terms of the physical position x and the given r and the speed v. Not a bad idea, actually, to think about that before you really start the problems. Is we're looking for this omega in terms of the given pieces of information and anything else. Let's see, what else did I say?
X.
And physical position x, yeah. You know, so here's your variable on position. So we're trying to describe this omega in terms of variable positioning x. What if x was really great compared to radius r? Let's say x is extremely great. If x is much greater than r, then what would you expect for the omega?
It'd be really small.
Very small, wouldn't you? Imagine this piston is way back off, this disc is way back off to the left, and this arm is laying almost flat here. And as this disc is being driven in at a constant velocity to the right, we're not expecting to see much rotation occurring if that x is really large relative to the radius, right? So we would expect a small omega if x is great, okay? Omega OA small. But clockwise or counterclockwise, given the direction of the velocity? Clockwise, okay. But clockwise. Okay. So these are the kind of little things you probably want to ponder as you're starting to set up, your investigation. Okay, so we've got an expression r over x we could drop in for theta. What about the cosine?
You can change it to a sine expression.
Just like we did in the last problem. Okay, so it seems like it might be useful to do that. Okay, so if we come in there, now what about x dot?
That's v.
Negative b.
That's negative v.
Thank you.
Negative.
Very good. Watch out for that. Always put, I highly recommend you always put little arrows on given pieces of information like that and definitions of positive sense. So you'll catch that very frequently. So we've got a negative v dropping in right there for that x dot. We've got our r over x popped in for our sine. We've got our x in here. Our cosine is going to be the radical of 1 minus our sine squared again, which is now going to become an r squared over x squared. And then here's our omega we're looking for of member OA, and that has to be equal to 0. Feel good? Oh, I see what you were saying. Yeah, you could solve for tan theta. Well, let's see, I don't like tan theta.
I use it for the square root of x squared minus r squared, and it worked.
Oh, yeah, okay. Yeah, that would work too. Okay. And so sometimes we just kind of go at it a less efficient way. Matter of fact, do you folks notice that when you solve problems? You maybe do pages of work, and then you get down there and you go, oh, damn, why didn't I try this back about a page before, right? You see that? That happens all the time. You get these insights. Huh? You get these insights by doing that, all that legwork you go through, you get these insights, and that's a real value of the struggles you go through in solving these problems, even when you're not solving them correctly. Okay. So, like we did on the last problem, we're just going to quickly drop in a common denominator inside here, and notice then that this x is going to cancel out with the denominator inside that radical, right? Okay. And then let's just leave this as is for a moment. So minus v r over x. Well, I'll take that to the other side. So we're going to end up getting the radical of x squared minus r squared times our unknown omega, and that's going to equal a positive now of this vr over x. And then we're going to kick this thing over into the denominator, and that should be our final answer. But I want to take a look at it before we believe it's correct and think about its behavior. Yeah, Alfred?
Factor of x.
Did I lose it?
No.
This guy reduces out once I do the common denominator in there.
No, see, they've reduced the final answer even more. They've only got one r
Yeah, they turned
term.
out.
Yeah, they factored I think what they do is they
From the square root, they factored out the r squared.
yeah, and then
Cancel out the r on the
Oh, I don't
and then
like.
they
It's
use
still
that.
the same answer.
I don't like their answer. This one's much better. Okay. Okay. Yeah. Yeah. Okay. So what we could do is we could divide top and bottom by capital R and then tuck that R squared back into the radical and you get their answer. Okay. Now, x is positive. This is telling us then that, and our v is given as a numeric value, and so this is telling us that this thing is,
It's going to be enough the closer
Yeah.
that disk
Because
gets.
X is going to get smaller.
Right, as X gets smaller, that link starts going faster and faster and faster, which makes sense.
okay,
X has to be less than R, though.
and x has to remain less than r.
Oh, that makes sense because it was vertical.
Yeah, x has to remain less than r. Okay.
In addition to this would be to give the disc or wheel a vertical offset.
Yeah, oh yeah. You can build these mechanisms up and give them all kinds of interesting, to alter the effects. And matter of fact, that's the way you do the design, is you might start with something like this, then you might go, hold it, this thing isn't really doing what I want it to do. I'm going to give this maybe a vertical offset, or maybe I might even make this wheel, like Daniel and I were talking after class the other day, maybe make this elliptical or some other cam shape. Pear-shaped or something, and you can actually force things to behave the way you want them to, and that's how you oftentimes do design. Old-style engineering used to do that. They would just build it, see how it behaved. If they didn't like the way it behaved, then they go, oh, I just need to adjust this a little bit. They make that adjustment, remachine it, try it, see if they get what they want. Nowadays, we usually do the analysis first, because it's less costly to do the analysis than it is to build the darn thing first. Okay.
In this
Yeah.
analysis of this problem, we didn't ever have to assume that the wheel was rotating. Just say it was sliding on there, right?
Well, it could be sliding with no friction, or it could be frictionless and rotating. It has nothing to do with the rotation. It has nothing to do with the rotation. Yes.
X greater than R.
Oh, x. Oh, thank you. Yeah, x must be greater than r. Thank you. We don't want to leave mistakes on this stuff, do we? If since it's being recorded. Okay. X has to be greater than r, so I'm glad you caught that, Ian.
That's just me.
Yeah. Okay. Okay. So good. Also checking to make sure everybody's awake.